Hello, I'm Sabrina Octaviani from Metallurgy and Materials Engineer, and I'm going to explain about step growth and chain growth polymerization. So, a brief overview of the type of polymerization. First, polymerization definition is a chemical process where a tiny molecule called monomers combine to create a larger molecule known as polymer. There are several distinct types of polymerization, each with its unique mechanism and practical use. And here's my summary of the primary categories of first is step growth polymerization. So, step growth polymerization is basically take place between monomers containing functional group that react in high yield to form new functionalities. Example of such functional group are carboxylic acid, which react with alcohol to form ester, with amines to form amides. And the step growth polymerization can be divided into first polyconsidrizing react to form polymers. Example include the creation of polyester and polyamide or nylon polymers. And the next is polyaddition. It's basically similar to polycondensation, but with no elimination of small molecule like water or HCl during the reaction. For example, is encompass of the formation of polyurethanes. And the next is chain growth polymerization. Type is basically divided into first free radical polymerization. So among the most common type, this is the process involved initiation, propagation, and termination process. So free radicals kickstart the reaction and extend the chain by adding the monomers until it concludes. The next is anionic polymerization. It's triggered by anionic entities like alkoxides or organolithium compounds. So this method is exceptionally controlled and result in polymers with low variation in chain length. The next is cationic polymerization. So it's initiated by cationic species like potent acids or Lewis acids. So it's frequently employed for creating polymer based on isobutylene. The third is ring opening polymerization. So basically monomers with cycling structure uncoil and interlink to form polymers. One instance is the ring opening polymerization of cycling esters, which yields polylactide or PLA from lactide monomers. And the next is leaving polymerization. So this technique enables meticulous control over the length and structure of polymer chain. Example, cover leaving free radical polymerization and leaving anionic polymerization that I already mentioned before. The next is ionic polymerization. It's basically a compass both ionic and cationic polymerization and determined by the charge of initiating species. And the next is coordination polymerization. It's a catalyst such as metallocans or Ziegler-Natta catalysts are harnessed to regulate polymerization of olefins like ethylene and polyethylene. The next is emulsion polymerization, and it involves polymerization within an aqueous environment facilitated by surfactant and commonly employed the production of latex paint. And the next is bulk polymerization that occurs without solvent or dispersant, often involving heat or high pressure. And the next is solution polymerization. It's basically transpire in a suitable solvent, offering control over reaction condition and polymer characteristic. And the next is suspension polymerization. Is monomers are dispersed in a non-solvent medium, yielding polymer particles, and this technique is used to manufacture materials like polyacetylene beads. So the second question is comparison between chain growth and step growth polymerization, emphasizing their mechanism and distinction. So chain growth polymerization is divided by initiation. So chain growth polymerization comes with an initiation step where an active species, often a free radical cation or anion, triggers the process by creating an active site on a monomer molecule, and it's commonly used initiators included peroxides in a free radical polymerization. The next is propagation. So during the phase, the active site on the monomer engage with another monomer molecule, generating a fresh active site on the resulting compound. So this iterative process continues with the polymer chain steadily adding one monomer unit at a time. So this is a swift and efficient process as polymerization advances without the need for additional initiators. So the next is termination. So termination is basically take place when two active polymer chains merge or when a chain react with an impurity, effectively halting further polymerization. So termination can lead to the creation of varied end group on the polymer chain. So it's depending on the specific of the termination process. So the next is characteristic. First is the chain growth. Polymerization typically unfold at a rapid pace, and it's well suited for generating high molecular weight polymer. And the next is careful control of reaction condition is often necessary of prevent termination and attain the desired polymer properties. So about step growth polymerization, first is reaction mechanism. The step growth polymerization encompasses a series of condensation reaction involving monomers bearing two or more reactive group. So this reaction result in the release of small molecule like water or HCl. So the polymer chain extend in a gradual, stepwise manner as monomer with complementary reactive group react with another. So prominent instance is include the synthetic of polyesters and polyalumates. So the characterization is first, step growth polymerization generally progress more slowly in comparisons to chain growth polymerization. The polymer's molecule weight it's not governed by the polymerization process itself, but instead by the stoichiometric balance of the monomers. The next is the resulting polymers often exhibit a higher degree of structural diversity and might possess a broader range of molecular weights. So it's often called polydiversity. And the difference between chain growth and step growth is polymerization is first mechanism. The chain growth polymerization involves initiation, propagation, and termination step, whereas the step growth polymerization comprise the successive condensation reaction between monomers. The second is reaction speed. The chain growth polymerization is typically swifter due to its rapid propagation step, while step growth polymerization progress more slowly due to multiple condensation reaction. The next is control of molecular weight. The chain growth polymerization allow for precise control of the molecular weight through initiation concentration, whereas step growth polymerization's molecular weight controls release under stoichiometric of monomer. The next is polydispersity. Step growth polymerization often leads to wider distribution of molecular weight, a higher polydispersity compared to chain growth polymerization. The next is N groups. Chain growth polymerization can yield various N groups on a polymer chain on the termination reaction, whereas step growth polymerization usually result in a fewer N group. And to summarize, the primary distinction between chain growth and step growth polymerization lies in their mechanism and the manner in which polymer chain extend. Chain growth is characterized by rapid and controlled growth involving initiation, propagation, and termination, while the step growth process is gradually through a stepwise reaction with elimination of small molecules. This variation holds significant implication for the properties and application of resulting polymers. So, how do initiators play a role in chain growth polymerization, and provide example? So, initiators play a crucial role in the chain growth polymerization process by initiating the formation of reactive site on the monomer molecules, which then enable the growth of polymer chain, and they are essential for controlling the polymerization rate, molecular weight, and other properties of the resulting polymer. Here's the example of the role of initiators in the chain growth polymerization, along with example. First is role of initiators. First is initiation. The first step in the chain growth polymerization is initiation. So initiators are compounds that can be decomposed under the specific condition, for example, heat or light, to produce highly reactive species such as free radicals, cations, or anions. These reactive species create active site on the monomer molecule, then it's allowing them to start polymerization. And the next is control. Initiators are very crucial for controlling the polymerization process by adjusting the concentration of the initiator rate, and the rate of the polymerization can be controlled. So the higher the initiator's concentration lead to the faster polymerization, while the lower concentration result the slower reaction. So this control allows for the precise tuning of the polymer's molecular weight and properties. And the third is termination. So initiators can also influence the terminator step. In some cases, initiators may participate in termination reaction, leading to specific end groups on the polymer chain. And termination reaction can be controlled or suppressed by proper initiator selection. And types of initiators is first, free radical initiators. These are initiators generate free radicals that initiate free radical polymerization. Common example is include first benzoyl peroxide as a compounds like AIBN, hydrogen peroxide, and organic peroxide. And the second is cationic initiators, and these are initiators produce cationic species that initiate cationic polymerization. And the example is Lewis acid, strong acid, and onium salt. And the third is anionic initiators. So these are initiators create anionic species that initiate anionic polymerization. And the example is include first alkali metals. Example is sodium and potassium. Alkoxide, and it's sodium ethoxide. The next is organolithium. It consists butylium. And the next is the example of everything is first polyethylene synthetic is in the production of polyethylene, a common polymer used in a plastic bag and container, and the free radical initiators like benzoyl peroxide is used, and the initiator break down upon heating, generating free radicals that initiate the polymerization of ethylene monomers. And the next is polyphenyl chloride. And the synthesis of PVC is a monomer polymerized using a free radical initiator such as AIBN, which is generate free radical upon thermal decomposition. And the next is styrene butadiene rubber SBR manufacturing. Use tires various rubber product and produced by copolymerizing styrene and butadiene monomers and initiator like organic peroxide and used to start polymerization reaction and control the properties of result in rubber. The next is living free radical polymerization. Initiators like alkyl halidase are used leaving free radical polymerization technique to control the polymerization with high precision. For example, is in atom transfer, a specific initiator is used to generate active specific that can be controlled to grow polymer with well-defined structure. In summary, initiators are very crucial in chain growth polymerization as they initiate formation of polymer chain control, the polymerization rate, and influence the property of resulting polymer. And the choice of initiator depend on the specific polymerization process and the desired characteristic of the polymer product. So how does the type of polymerization, chain growth versus strep growth, and the influence of properties and application of the resulting polymer, and how to polymerization method impact polymer properties like molecular weight, branching, cross-linking, and how these properties correlate with specific application. So, the type of polymerization method, whether chain growth or step growth, has profound impact on the properties and application of resulting polymers. The discussion on how this method influences various polymer and their corresponding application. So, first is molecular weight. The chain growth is the polymerization typically allow for more precise control over molecular weight. By adjusting the initiator concentration, the rate of propagation can be controlled and leading to polymers with well-defined molecular weight, and this precision is valuable in application requiring polymer with specific size distribution such as the electron industry for semiconductor and optoelectronics. So the next is step growth. Step growth polymerization is less effective at controlling molecular weight. The molecular weight of the polymer depends on the stoichiometric ratio or monomer. This often results in a wider distribution of molecular weight or polydiversity. These polymers are used in application where polydiversity is acceptable for such as in the production of adhesive and coatings. The next is branching and cross-linking. So chain growth polymers typically have linear structure with few or no branch or cross-link, but however, copolymerization can introduce the controlling branching or cross-linking which can be tailored for specific application. For instance, cross-link polyethylene PEX is used in plumbing application due to its enhanced the chemical resistance and mechanical properties. The next is step growth. Step growth polymerization often have a higher degree of branching and cross-linking because the reaction involves the simultaneously coupling of multiple reaction groups. So this leads to the formation of three-dimensional networks in some cases. And step growth polymerization with extensive cross-linking are used as thermosetting resins in composite where heat trigger curing is desirable. So the next is thermal properties. Chain growth polymers typically have better thermal stability as they are less likely to contain labile group prone to thermal decomposition. This makes them suitable for high temperature application such as in automotive parts and aerospace component. And the next is step growth. Step growth polymer can contain more labile functional groups due to the condensation and reaction involved. This group can lead to lower thermal stability, but however, step growth polymers can also be tailored to have excellent thermal properties, as in polyamides used in electronics and aerospace industries. And the fourth is processing characteristic. For the chain growth, polymer often have superior matte processability due to their linear structure. They can be easily melted and molded, making them suitable for applications such as injection molding, extrusion, and 3D printing. But for step growth, especially highly cross-linked one, may have limited melt processability. They are often processed through technique like comparison molding or resin transfer molding or RTM. Their processability can be enhanced by introducing thermoplastic component into the formulation. The last is application. For the chain growth polymers, find application in wide range industry, including the plastic coating and polyethylene, polypropylene, and polystyrene used in everyday plastic. The next is step growth. Step growth polymerization are used in application where specific properties such as adhesion, high temperature resistant, chemical resistant are required. Example included polystyrene used in textile, epoxy resins in adhesive, and polyamides in electronics. And then, in summary, the choice between chain growth and step growth polymerization significantly influenced by application of polymer. Chain growth polymers are known for their control molecular weight and excellent melt processability, while step growth polymer often exhibit branching, cross-linking, and unique thermal properties. And the selection of the appropriate polymerization method depends on the desired characterization of polymer and for particular application. Thank you so much. I hope my video is insightful and I hope I can learn about the polymers more and more from your lecture and from my video. Thank you. Have a nice day.